How are you? Everybody is okay? Okay, good. I was scared. You just let me know. Final is coming. So you will have a final this week? Some final this week? 2. Wow. Wow. I see. Yeah, you know what? Just in more weeks and everything will be done. Okay, and we can enjoy much deserved summer. Okay. Hopefully, by that time, the country is open again, and we can at least go out a little bit. I think. Okay, so let's see. Yeah, let's wait just one more minute, and we can start. Okay, let me. So I remember about an hour ago, I sent you an email, right, just for a few reminders. So hopefully it is clear to everyone. And I try from my side, I try my best to minimize the mistake from you. For example, wrong spelling, all these things. But I expect you to try to minimize the mistake from your side as well. Okay, so as I said, if a question is about code writing, then I will grade manually. However, if it's not code writing, then it will be multiple choice. Not multiple choice, but will be graded by automatically. Okay, so be careful. So bring the blank pages to do the calculation. Check your results carefully, very carefully, okay, before filling in the box. And follow, in any case, strictly follow the instruction from the question. Okay. For example, if the question tell you to fill in 4 binary digits, then do so. Don't fill more than that. Don't put 0 in front of it or whatever. So just if it's 4, then 4. Okay. And don't insert spaces in between the binary digit, for example. So as I said, please follow the instructions. Okay. So with that, let's see if you have any question, logistic question at the beginning, so I can answer that before we go into the material over here. So let's see. So William has, I will try the best I can. Mistakes and all. Okay. Yeah, try your best, okay? Try your best. And I make the exam a little bit easier to compensate for that, okay? Just a little bit easier, okay? To compensate for the fact that you have to spend time to check your answer carefully. Okay, so any other question before we review all the chapters again? So let's see. Okay, so seeing that you don't have any question, so let's start. As I said before, the final exam will be comprehensive. So everything. So let's start from chapter 1 first. So of course you are responsible for not only for the slides, but also for reading the textbooks and also for homeworks, everything. Okay, so let's start with chapter 1. Of course, I just focus on the important things. Okay, the things that I really want you to know before graduating from EE120. Okay, so it has there are a lot more topics that I didn't mention, but you should know. You should know which one is important. Okay, so these are just not everything, but at least we cover most of them, most of the things that I like you to pay attention to. Okay, so first of all, about the variables, right? So I think this slide summarizes well in terms of allocating variables in the memory, right? So over here you can see that for usually for global variables, um, or static variable, for example, right? It usually go to the initialized data area down here. Okay. If for global variables that are initialized and static variables, it will go to here, to the initialized data region over here, right? So for the uninitialized global variable, it will go into the zero initialized data. So compiler will allocate the memory for you and also initialize to zero for you, right? If you forgot to initialize them, okay. And then during running a program, right? If you allocate memories on the flight, right? So it will use the area in the heap area over here, okay. And remember, whenever you call this, you call a subroutine, something like that, then the parameters or the local variables of the function will go to the stack, okay, the stack here, and that area will grow down, okay. So so heap grows up, stacks go down, okay. And just remind you, okay, sometimes for performance reason, the compiler sometimes allocate a variable using a register in the processor, and you know that the registers, the number of registers in the processors is very, very limited, right? So we, for example, for the Cortex M0, M3 that we are studying, there are only 13 general purpose registers. So only in case of performance, then the compiler sometimes will allocate the variable using a processor register. Okay, for example, loop variable, for example, right? Okay, so what else in chapter 1? But do you have any question for chapter 1? Hopefully not, right? Easy enough. Okay, so if you don't have anything to ask, so let's move to chapter 2. Okay, chapter 2 is about numbers, representations. So for positive numbers, right? For positive numbers, you can use unsigned binary number, okay, to represent it. And the range for the unsigned integers is from 0 to 2 to the end minus 1, right? That's easy, right? So if you have an 8-bit unsigned binary number to represent integers, then the range is from 0 to 2 to the 8 minus 1. So that will be from 0 to 255, right? 255. So for unsigned number, okay. How about for signed number, right? So for signed number, actually for signed number, it means that you have to represent the negative numbers, right? So how to represent negative numbers using binary bits? So there are 3 ways, right? 3 ways. Either size, magnitude, we already learned about it, or 1's complement, or 2's complement. Okay, so there are 3 ways to represent negative numbers, but of course the most popular one is 2's complement over here. Okay, so maybe if you pay attention over here, you pay attention to the ranges over here for me. Okay. Okay. So I mean, especially for 2's complement over here. So for example, just for example, maybe answer for me. By this time, you have to answer very, very quickly for me. Okay. Okay. So for example, if n is 5, okay, for 2's complement number, what will be the range? Very quickly. Go ahead. If n is 5. What is the range? Wonderful. Right. Yes. Christian is correct. William is correct. Wonderful. Yeah. Wonderful. Including, okay, from minus 16 to 15, including minus 16 and 15. Okay. That's good. One more time, just do one more time. 8 bits, okay? 2's complement, 8 bits. Quickly. Okay, wonderful. Yeah. Oh, William, be careful, William. Minus 128 to 127, okay? William, be careful, okay? Remember, you see the power over here? N minus 1. So raised to the power of 7 in this case, okay? For n side, with a bit, you raise to the power of 8. Yeah, so be careful with that. Okay, so let's move on. So chapter 3, maybe we can skip that one. I hope that you, chapter 3, you have to know that one, okay? I don't really review over here, but you have to know. For chapter 3, I think that we learn about, what is that? The directives. Directives are important, okay? So for you to actually to read the an assembly program, right? So be careful with that. So reveal the directive portion for me. Okay, so let's move to chapter 4 over here. So chapter 4, of course, there are tons of instructions, but I just mentioned about a few of them over here. Okay, a few important over here. So you have add with carry, subtract with carry, reverse subtraction, multiply, and accumulation, something like that. I mean, and side division, unside division, and the saturation, and size saturation, and unside saturation. Size saturation and unside saturation are usually used in digital signal processing application. Okay, so sometime, for example, in that area, in that application area, they use to increase the performance. Okay, they use a lot of instruction called SIMD instruction, called single instruction, multiple data. Okay, so sometimes just one instruction, and you can add or you can subtract four calculation at the same time. Okay, so sometimes you have to to have more bits for the sum, for example, right? But at the end, and when you do summing or subtraction, sometimes you actually go out of the ranges. Okay, you can the sum or the difference can overflow. Okay, so in this case, we really have to use the saturation operation to minimize the distortion of the sounds or the picture. Okay, so just to remind you, for the DSP application. Okay. Okay. So another one is I really want you to pay attention. What is that? Well, William has a question over here. Let me see. To verify, would these table be provided like our previous midterms? As I said in the email today, I will probably provide you a very small table, maybe this much, okay? To basically to specify all the instructions used in the final exam, but some other instructions, I didn't put in the table because I expect you to know. I expect you to know, at least if you go through the review document over here, you should see these instructions. I don't need to put into the table, okay? So you have to know that one, okay? For example, I mean the loops, things that associate with loops. For example, branching, compare, something that you really have to know. I don't need to put it in the table, but you should know that one. I mean, load, move, all these things. Okay. Okay. So next thing is bitwise logic. This is very, very important. Okay. So I don't think that I will allow you to graduate from EE120 without knowing how to manipulate bits, manipulate numbers at the bit level. Okay. Okay. So, and you already know how useful it is. in the labs, right? So sometimes you really have to turn on this bit to, for example, you have to configure a general purpose I/O to be an input or output, right? You by turning on one bit, the bit for that pin to 1 or 0, right? So it is extremely common and useful for embedded engineers. So I really require you to know about the bitwise logic over here. Okay, so you have AND, you have OR, you have XOR, all these things. Bit clear, right? Bit clear is very easy. It's basically you just AND with the inverse of the operand number 2. Okay, so it related to what I will say on the next page, and then bit field clear, bit field insert, and then something like that. Okay, so these, especially some top instruction over here, they are very important, and I put a truth table over here. Okay, so before I turn to the next page, let me read the question over here. So just focus on the tables that are in the reviews. Oh, the tables in the review are the most important thing, but you should know everything. Okay, Matthew, you are expected to know everything in lecture, in slide, and in homework. Okay, so I keep repeating that one again and again. Okay, so the next, let's go to the next page over here. Okay, so to manipulate bits, okay, what do you use? Usually, what do you use? You use bit mask. Okay, understand? So, for example, if your number is 8-bit number over here, okay, and if you really want to do something with bit 4 and 5, remember the bit start from 0 over here. 0, 1, 2, 3, so 4, 5 over here. So if you want to do something with bit 4, 5, you have to create a mask, okay? And after you have a mask, you can do whatever you want to do with bit 4 and 5. You can toggle them, you can set them to be 1, you can clear them to be 0. So the first step is create the mask, okay? And creating the mask is very easy, right? If you really want to manipulate bit 4 and 5, so your mask will have a 1 at the positions 4 and 5. That's it, okay? The number of bits for the mask is the same as the number of the binary number that you want to manipulate, okay? So 8-bit over here, the mask will be 8-bit over here too, right? And 1 over here is to specify the bit position that you want to do something with it, okay? So now let's use the mask over here to manipulate the binary number n, right? So if you want to check a bit over here, right? So your mask may be just 1 bit 1 over here, right? So you can end with a mask and then check the result to see if the result is 0 or 1, and you can determine if that bit is 1 or 0, right? So if you want to convert, in this case, for example, if you want to convert bit 4 and bit 5 of the binary number n to 1, basically, if you want to set these bits, then what do you want to do? You just OR with the mask, okay? You just OR n with the mask, and then you can see that bit 4 and 5 for number n will be set to 1, okay? So how about if you want to clear bit 4 and 5 of n? Then you will end with the inverse of the mask, okay? Okay. How about if you want to toggle bit 4 and 5 of n? Then you will XOR, okay? You will XOR n with the mask, and that's all. So this is a very short sentence. I put it over here for you to remember, okay? So to check a bit, n with the mask. To set a bit or a few bits, right? All with mask. To clear a bit, n with the inverse of the mask. And to toggle a bit, XOR with the mask. You remember, in this case, in the example over here, your mask have 2 1 bits over here, okay? So whenever you can clear these 2 bits, right? Or you can set these 2 bits, you can toggle these 2 bits, okay? Not just 1 bit. You depend on your mass. Okay. So let's move on. So for barrel shifter, I think that we already learned about this one several times, and even I remember even in the midterm, I had a question for this one. Okay, so I think that with that we don't need to spend time on this anymore. I just put here to remind you. Okay, before graduating from 120, you should know about this thing. Okay. So let's move to the next page, so chapter 5. So chapter 5, of course, I like you to know about Endianness, right? And by this time, you should know, okay? So I don't need to come back and tell you again. So you should know this one by heart. You should know about accessing the memory using the post-index, pre-index, and pre-index with updates. Okay, so be familiarized yourself with these instructions again. We learned about this one again and again already, and you also learned about this one already. So I don't really want to spend more time on this one. Only a little bit down here. So for load and move command, these instruction can be used to load a constant into a register. Okay. So for example, in this case, for the load or move, the effect is the same. For load over here, I want to load the constant FF to R0, right? The move instructions, you can use the same thing. So FF move to R0 over here. However, the syntax is different. Okay, so for the K of load, you can see that we use an equal sign over here. Okay, but for move, this is a pound sign. Just that. Just be careful with that. Okay, so let's move to chapter 6. For chapter 6, that's a condition, right? So what do you have? You have a branch instruction, right? Branch if it equal, branch if not equal, unconditional branch, like I remember in some loop construction, right? You just branch to loop, basically to look back, and so you use the branch in the instruction over there. So, and we already learned about this one carefully. So I don't really want to spend time on this one anymore. But pay attention, okay? Otherwise, you cannot writing or reading the assembly code. Okay, so be careful. So for example, just for example, this is very common. So in this example, you compare register R1 with register R2, and if they are equal, then you will branch to some label over here. Okay, some other instruction. Okay, and this one is very useful too, right? So if you use a shortcut over here, whatever you use CBZ, in this case means that you compare and then you will branch. Can you wait for me just a few minutes? Just 10 seconds. Okay, I'm back. So this one is compare and then branch. If the register equal to 0, Z means 0. Okay, so compare R1 with 0, and if it is equal to 0, then you will branch to the label over here. So this one is equivalent to the 2 over here. Okay, just a shortcut. And this is just the same thing, but this is a branch compared to 0 and branch if not equal, and that's all. So learn about that. And for loop construction, of course, you have to know. I have to warn you. I mean, that you really need to review this one again. And if it's hard to remember, put in the cheat sheet for me. Okay, for this, just put it in there so that you don't forget. Okay, so and then chapter 7 we have a tons of example when you use these construction loops, ifs, else, and to write a program, to a complete program. And also it's good to learn about some algorithms to do something useful. Okay, so if you have time, review that one for me. Okay, so we move to chapter 8. Chapter 8, we also already have the exam on it. So just a few reminders. So if you want to jump to a subroutine, right? So usually you use the instruction branch and link, right? BL, branch and link to a label, right? To a function, a subroutine, for example, right? So and the instruction address, the address of the next instruction will be stored in the LR register to remember where you should return after you're done with the subroutine. Okay, so when you're done with the subroutine, you can use the instruction BXLR to jump back. Okay, so the effect of this one is to copy whatever value in LR into the PC for you to jump back to the main function, okay, to the calling function. Okay, there's also another. Don't forget, there's another way to return from a subroutine, right? So what way is that? That's the pop PC. Okay, so instead of BXLR, so at the beginning of the function, you save the value of LR into the stack, right? You save it there. So at the end of the subroutine, you pop that address out and put in the PC, right? And if you put the return address in PC, the processor will jump to that address, right? So that's going to be correct. So in this case, the effect is the same. Okay. So let me repeat again. To return from a subroutine, you can use pop PC, right? If you already push LR value to the stack before at the beginning of the subroutine. Okay, so at the end of the subroutine, just pop that one up and put it in PC for me. Okay. Okay, so wow, review this one carefully for me. Okay, push and pop. You really have to know that, and push and pop is very easy. For the stack, remember, you will grow down. Okay, grow down when you push the data in there. So when you pop, the stack pointer will go up. Okay, so just review this one carefully for me, because this one related to chapter 11. That you whenever you have to execute an interrupt service routine, you really have to remember how the A register are pushed into the stack and pop up. That's very important. Review that one for me. Okay. Okay. So let's move on. So in chapter 8, we also talk how to pass the parameters to a subroutine or function. So remember to use register. Usually you register R0, okay, to pass the arguments to the function. But if the function requires more than that, you can use R0, R1, or even R2, or even R3, right? But if it's more than R3, then you start to use the stack, okay? You start to pass the parameters, additional parameters to the stack, and then the subroutine will take the parameter from the stack, okay? And then for the return value, the subroutine will put the return value in register R0, or if it has have more, or if the return value is more than 32 bits, then it can use R1, R2, and R3 as well. Okay. Okay. So and this is also important. The push and pop over here. I put the example over here to remind you that if you push in the order in the curly bracket over here is not important. Okay, because the processor actually already sort the register before pushing to the stack. So it will push for push operation, it will push the higher number register first. Okay, in this case R6 and then R5 and then R4 over here. But how about for pop? It will pop out. It will pop out from the stack and put in the low number register first. So in this case, you pop out the stack and put the value in R4 first, and then R5, and then R6. Okay, so just remember this this order from. Okay, so at the end of chapter 8, I think it's there's one of the maybe the probably the most difficult subroutine. I have to say so for you. Maybe some of you is actually it's very natural. It's easy, but for me, from my experience, probably students usually have a problem with the recursive function. Okay, so I think that at the end of chapter 8, there is a very good example for a recursive function. That's a factorial. It's a very kind of basic example to illustrate the recursive function. So recursive function, if you look at over here, how can you recognize a recursive function? Can you tell me? In this case, you can see that there are two functions over here, right? One function is the main function over here, and another function is actually the factorial over here. Is this function is actually a recursive function, and the way to recognize it is this function call itself. Do you see that? Function factorial over here. So you go down, you execute the function, and at some point, it call itself again. It basically go back to this instruction again. So that's the way to recognize if it is a recursive function or not. Sometimes it doesn't really directly call itself, but it call, for example, if function A will call function B, and then function B call back to function A. Okay, so that one is also recursive as well, but it actually a little bit more advanced. Okay, so maybe in this class, if you see something that a function that call itself, then it is a recursive function. Okay, and then try to look how to trace this one from it, to try to see if you understand what is pushed into the stack over here, right? To see if you understand. Just trace by yourself. It's very simple. Just a few command over here: push, move, compare, branch, not equal, and then pop, and then look. Okay, so everything you already know. So then let's trace a very short assembly subroutine, right? And be sure you understand. Okay, so next one, chapter 10. Okay, let me wait for seem that somebody had a question over here. So just focus. Oh no, Matthew. Oh, that's the old question. Okay, let's see. Okay, so if there's no question, let's move to the next chapter, chapter 10. Oh, so William has a question. So the exit is look up. Okay, let me move back. Okay. Yeah, let me move. Let me zoom out to see. Ooh. Okay, so multiply, bring here. Yes. That's how you exit. That's how you actually even. Let me see. Let me see. For the PC. Oh, actually not William. Actually during the loop, right? During the loop, it actually pop R4 out, and R4 is stored in the stack over here. Okay, so when it pop R4 out, okay? So, and then also pop PC out as well, right? So PC, you can see in this case, PC sometimes 158. So remember, 158 is here, right? So when it pop out R4, it take the R4 and multiply by the basically accumulate over here, right? 3 multiplied by 2 multiplied by 1. So this loop is actually just accumulate, not accumulate, but multiply back 1 and 2 and 3, okay? And after that, at the very end, okay, when it pop out the 134 over here, okay, and it initialize for PC, it is at the time it actually quit the loop and go back to the main program. In this case, is 134. Remember, you call factorial over here, right? So when you pop to this area to pop to this data, then it will quit the function factorial and come back to this command. Okay. This one, the stack may be very long, right? So in case if you enter not number 3, but if you enter number 100, you will see that it will push in a lot of value over here. Okay, it will push in 100, 99, 98, 97, right? And then the loop here, when it pop over here, it starts to pop out one by one and accumulate the product at that time, right? But at the very end, when it pop out the PC 134, it will jump back to here. Okay, so that's what it is. Is that okay, William? Okay, wonderful. Okay, so let's go to chapter 10. So what is in the chapter 10? So for chapter 10, I would like you to understand all of these things. Data alignment, okay? Why do we need data alignment? So you should answer that question, right? What is the advantage? I'd like you to understand the static variables, right? Right? Static variables is sometimes we put in, remember at the very first slide, I told you that static variable will be allocated in the initialized area of the memory, right? So it is in the memory. So whenever you want to do something, you have to bring it into the processor and do it at the end. You have to bring back to the memory. That's why static variable can remember the value between function calls, okay? Because it's in the memory, okay? So just remember that. And then in chapter 10, we also have examples for a C program to call assembly, and then also assembly program to call C program, right? So just remember that. So because in your software engineering teams, you may have 100 engineers. Some of them, maybe 95 of them will write C programs. But for you, because you are good at assembly language, maybe your boss will assign you to write a very critical function to improve the performance. So in that case, you will write some assembly, right? And your assembly routine, subroutine, or function will communicate with the other function that your friends develop. Okay, so just remember that. Okay, so with that, 10 is okay. So let's move to 11. Okay, interrupt. Okay, so what do we want to do to know about the interrupt? Is interrupt useful? Very useful, is that right? Right? But what is interrupt, basically? So if you have, after this class, if somebody asks you again, what is interrupt? At least you have to remember something, right? So maybe the very first one thing is sometimes you have to interrupt the processor to do something, right? The processor can run a program, and then sometimes you have to, for example, if you really want to communicate with the processor for like pressing a button or something like that, you like the processor to recognize that one and to do something for you, right? So in this case, you interrupt, something like interrupt the processor, okay? So that's what interrupt is used for communication between the processor and the peripheral devices, okay? So and you can see that one of the very good example is a timer, remember? So the timer can generate the interrupt and then can tell the processor to do something periodically, right? So for example, if you can set the timers for the timer to generate interrupt every second, you can interrupt the processor every second to do something. For example, every second you will tell the processor to turn on a LED or something, or take a picture or whatever, right? Or sample for ADC, for example, or sample an input, for example, right? So that's maybe just remember that, or maybe you can use the interrupt to deal with some situation happening locally. For example, if you divide by 0, then you want you want to raise an interrupt for the processor to deal with that situation, for example, right? Or maybe you can use interrupt to for later on for multitasking, for example, right? So these are the applications that I would like you to know. And then also there are, for communication between processor and peripheral devices, there are actually two ways, right? Either you use interrupt or you use polling. Polling is less efficient, because polling is basically you require the processor to pay attention to the peripheral device to see if the peripheral device wants something from the processor. For example, you want to send some data to the processor, and then you have to write the software for the processor to just constantly looking at the port to see if there's data coming or not. And then during that time, the processor cannot do anything, because it just sit there and then pay attention to the port to see if there is a data coming, right? So, but however, for interrupt, it's a little different. Interrupt is the processor can do whatever it wants, right? So whenever data comes to the port, you just raise an interrupt to tell the processor, hey, processor, data just comes. Please stop what you are doing and take the data in for me. Okay, so you can see in this case, interrupt is more efficient, right? So the processor doesn't have to waste its time. It can do whatever it wants. So whenever the peripheral devices need something, it will knock the processor by raising the interrupt, right, for the processor to serve. Okay, so the sequence over here, I think, is a very good sequence over here that I like you to know. For example, when does the processor running the main program over here, and by this time, at this time, some peripheral devices or even internal device notify the processor it needs something, right? Raising an interrupt. So the processor will stop what it is doing, and then it will do what? Do you remember? It will automatically push into the stack A registers. Okay, don't forget these are A register. R1, R0, R1, R2, R3, R12, LR, PC, and PSR. Okay, that's the very first thing. The second is it had to find to run a interrupt service routine, right? To run a subroutine. So it had to find where the subroutine is by looking at the interrupt table. The interrupt table has the address of the subroutine, right? So it look at the interrupt table, find the address of the subroutine. So at that time, when it finds the address, then the PC will point to the first instruction of the subroutine. Okay, the PC here. The PC will not point to the instruction in the main memory anymore. Okay, just remember that. Okay, only when it return back here, then the PC will be restored. The address in PC will point to the next the instruction of when the interrupt happened over here. Okay, so just remember that. Okay, so when it returns from the subroutine over here, the interrupt, the ISR, then it will pop out A register. Okay, so so you have to know these A register. Where do they go? Where do they go? So they can go to the main stack, or they can go to the process stack, right? Remember there are two stack, okay? Two stack. So and two stacks depend on what? Depend on the mode over here. Okay, so look at the control over here. Okay, look at the control over here. So right before the interrupt happen, right? So if the control bit is 0, for example, then it says that the program is using the main stack pointer, and then the A register over here will go to the main stack pointer. Okay, so when you pop out from the main stack pointer. Okay, but when it is interrupted in the main program over here, at that time, if the control is 1, it indicates that the program is using the process stack point, process stack, right? So this A register will go to the process stack instead of main stack over here. Okay, just remember that. Okay, so and the second, okay, and this the second thing I want you to pay attention when for the auto stacking and auto unstacking is the value you have in the LR in the link register. So remember, the link register has two purposes. Okay, so usually if you use the link register for the subroutine call, for example, BL, right? So in this case, the link register contain the return address in the calling function. Okay. However, for interrupt, right, interrupt service routine, the link register doesn't actually contain the return address. Okay, but it either contain this value or that value. Okay, depend on here. Depend on right at the beginning of the interrupt. Okay, if you use main stack pointer, okay, then the value in the LR will be F0 over here, F0. But right before calling the interrupt service routine, if you use the process stack, okay, then the value in LR is FD. Just remember that, only two values. Okay, so at the end of the service routine, interrupt service routine, it will the processor will load this one, will look at this one to know in from what stack you will unload this A register. Okay, unstack this A register. Okay, and when you unstack this A register, do you remember you have a PC value in it? Okay, and that PC value will tell the processor where to go back to the calling function. That's all. So that's the main sequence for you to understand. So so please review carefully the example on slide 14 to 23 for me. Knows everything in that in this slide in chapter 11 for me. Okay, right. So one more thing is, I just tell you about the table, interrupt vector table over here, right? So you can see this is the interrupt vector table. That's the slide number 6 in the chapter 11. So remember that in the PSR register, whenever interrupt happen, then you probably you know what kind of interrupt has happened, okay, by looking at the number over here, okay. But remember, this number is a little bit different from the interrupt number over here defined by the CM SIS, okay, so Cortex M software interface standard, okay. So they are not exactly the same. There's an offset of 16 over here. So just remember that the number here is different from the CM SIS number, okay. Okay, so anything else? Oh, of course, I mean, you should learn about how to disable an interrupt. For enabling a peripheral interrupts, usually you use a register, okay? And of course, one bit is for one register. For example, if you want to enable interrupt 27, okay, so you should turn on bit 27 of ISER0 register. Okay, so let me ask you, if I want to enable interrupt number 42, then what bit you should turn on? You should turn on the bit number. Wow, it's very hard for me to see. Let me zoom out. Okay, you should turn on bit number 10 of register ISER1, right? Very easy, okay? Okay, so let me move on with the interrupt over here. Interrupt priority levels. Please review that one too, right? So remember, for the interrupt priority, if they has higher interrupt priority number, means that that interrupt is less level of urgency is actually less, right? Just remember that. So you have a homework problem for that. Okay, so let's move to the next slide over here. Oh, okay, this is a huge, very, very important chapter that I would like you to know as well. Very important, okay? So for fixed point and floating point number, basically just two ways. I just focus on two ways to represent real numbers using binary bit over here, okay? So if I ask you, for example, if you have this kind of bit sequence over here, remember in memory you don't have the radius point over here, okay? This is just for you. It's easier for you to understand. But in memory, of course, you don't have this one. You just have a bit over here, okay? And if I tell you these a bits represents a fixed number in the format in the unsigned fixed point number with n bits to represent the fraction part, right? So in that case, I like to ask you, what is the real value, the real decimal value that these bit sequence represent? Can you do that? Because this sequence look like then you should do like this. You should say, in this case, unsigned, right? So you should say that, oh, if this is an integer, so this bit pattern will represent what unsigned integer, right? You should ask you that. And this one turned out to be 109. Okay? So the integer pattern represent 109, right? So the real numbers, it represents actually 109 divided by this. So divided by 2 to the, in this case, if n equal to 3, so you divide by 8, and that's the real number. Okay? You have to be very quick in this case, okay? I think that this formula is very useful, okay? Just assume that this is an integer over here, okay? An unsigned integer, okay? Assume that, find the value for that unsigned integer, and then divide it by 2 to the n over here, and that's the real number, okay? So similarly for sign, so if you have a binary number like that, okay, and somebody already tell you, oh, this is actually a fixed sign number in the QM.N format, right? So then I ask yourself, I'd like to ask you, what real number it represents? Can you answer that question, right? So same thing. You just look at this binary pattern over here, right? And try to figure out the value for that two complement binary. Treat it as a two complement number, okay? So in this case, you can see clearly this is a negative 109. Is that right? right? Remember, this one is a minus 128 over here, right? Minus 128 plus 16, right? Is what? Is minus 112, right? And then also plus 3, plus 2, plus 2 over here. That will be minus 110. And then finally, you also plus 1 over here, right? So that's the minus 109, okay? 109. So remember the way over here. 1, 2, 16, right? 1, 2, 4, 8, 16, 32, 64. But the last one, the side bit here is minus 128. Okay, so remember that for side. Okay, and after you figure out the integer value for the 2's complement number, then just divide by 2 to the n. So let's see how many bits for fraction over here. Raise it to 2 to that 2 to the n, right? And then minus 109 divided by that. So in this case, n equal to 3. So you just divide it by 8 over here. And the true number, the true real number, this binary pattern represent is actually minus 13.625. Okay, so just go through the homework for this one for me. And for this slide, I put it over here for you to go in the reverse direction. So in case if you know the true value, the real value over here, right? So how to convert this one to a fixed point binary number, right? So this is a way to tell you how to go back. Same thing over here too. So in this case is psi fixed point, right? How to convert a real number over here, positive or negative, right? To this format over here. So look at this example to try to understand that one as well. Okay, and the ranges, right? The ranges. Do you know how to calculate the ranges? The range, for example, for unsigned number, right? Unsigned number is basically the integer ia over here divided by 2 to the n, right? So assume that n equal to 3, for example. So basically over here you divide it by 8, right? Okay, so look at over here. So what is the range of unsigned integer for 8 bits over here? So that's from 0 to 255, right? But because you divided by 8 over here, so the range for the fixed point number will be from 0 to 255 divided by 8, right? Understand? And then so that's very easy, right? So look at over here, you can see that this is for unsigned, it is like this. So for signed, you should divide by 2 to the n. And that's the range for unsigned. For signed, similarly, you divide it by 2 to the n over, divided by 2 to the n. Okay, that's it. Okay, so now let's move to the floating point. Okay, we just learned about fixed point. Now learn about floating point, the second representation. So for this one, just remember if you see a floating point number, for example, a 32-bit over here, right? So if you see a binary sequence over here, how do you calculate the true value, the real decimal value from this one? How? Just remember this formula for me, okay? So this bit will tell you the positive or negative, right? The second is look at the fraction over here. Convert that fraction into the real number, but don't forget to add 1, okay? And lastly, look at exponent over here. Don't forget to subtract the bias, okay? So for the case of 32 bits, the bias is 127, okay? So maybe for the example, I think that please review carefully the examples on the slide 24 to 33 of chapter 12, okay? Try to learn everything about it, Okay, and also like to you should know about converting a real number to the floating point number too, right? Okay, in this case, so learn about this one. I mean, you have to do as quick as you can. So in this case, first of all, you have to put into the scientific notation first, right? So you have to put in the form of 1 point something, right? So if you want to put in this form, you have to divide some power of 2, right? So either you divide it by 2 or 4 or 8 or 16, something like that. So in this case, the closest value to 14, right, is actually 8, right? So that's why you should divide it by 8 in this case to get 1.8 something. And because you divide it by 8, you have to multiply by 8 over here, so that the value on the right hand side will be the same as the value on the left hand side. So put in this format for me, okay? Put in this format, and then you can put a hidden one over here, and then the true exponent you already have over here, okay? So now you can convert this one to the standard IEEE, right? By what? By, first of all, by convert the fraction here to binary. So how to do that? This procedure you have to know, okay? I remember that in the homework, I actually typed the solution by myself for, I think, the homework 12 or homework 11 or something, just to emphasize that you should know in this case. So the fraction in this case is 0.8125, right? So keep multiply by 2, right? So when you multiply by 2, you will express in this case, you will express 1 plus some fraction, or sometimes it's 0 plus fraction over here. So this digit over here will represent the fraction over here, okay? So in this case, 0.8125 multiplied by 2, you will have this one. And you take the fraction over here, continue to multiply by 2, so you have a second digit over here, 1, right? And the fraction is here. You take the fraction here, multiply by 2 again, you have 0.5. And 0.5 is actually the digit before the radix point, the decimal point is 0. So that's what the next bit will be 0 over here, okay? And 0.5. And you take the fraction here and multiply by 2 again, you get 1. Okay, so in this case, so that's why the fraction binary representation for the fraction is 1, 1, 0, 1. Okay, over here, 1, 1, 0, 1, and the rest could be 0, right? Because up to this point, 0. So remember how to convert from the real number to this one, okay? To the standard IEEE 754. So in the slide, actually there are good examples for 8 bits, right? Pay attention how to convert a real number to 8 bits, 8 bits floating point, okay? Just for example, right? So in reality, we only have 16 or 32 bits, but maybe to illustrate the point in the slide, we just assume that there is an IEEE 8 bits floating point number, okay, for you to understand. Okay, so there's a question over here. Let me try to answer. Does it always have to end up exactly 1 to stop? No, it doesn't have to. So for some number, it can go past 23, right? Remember the fraction in this case has 23 bit, right? 23 bit for a fraction. Okay, so if it goes past 23, you stop right there. Basically, you just truncate the remaining bit. Okay. Okay, understand? Okay. So, some useful special floating point number in this case. So if you want to represent 0, you just put all 0 over here, okay? And the side bit can be 0 or 1. So that's for 0, you can have either representations, okay? For positive infinity, you can represent that one too. So put for the fraction part, put 0 or 0. Exponent part or 1, but the sign is 0, okay? For positive infinity. For negative infinity, you have all 1 over here, including the side bit over here, but the fraction is 0. Okay, so just remember these special representation, special number over here. Again, let me please review carefully the example on slide 24 and 233. Okay. Anything else? Okay. Lastly, the timer. Timer. I remember I reviewed very, very carefully for you in the lectures, in 2 lectures themselves. Okay. I practiced with you, so so please, it is not hard at all, right? So remember, the timer that we use is a 16-bit timer. Okay, 16-bit timer, and the clock to clock the timer counter directly is represented in here, right? This one. That's why I put this clock CMT over here, right? But that clock actually comes from another clock over here, okay? Another source clock, and whatever it is. I mean, usually you can pick from 3 different sources or even external clock over here, and you can use this prescaler to divide the frequency down to here. Okay, so understand? And then I may ask you to generate these waveform, right, with a certain period and duty cycle, for example. So you should know, right? So in this case, duty cycle is what? Duty cycle is equal to 1 plus ARR, right? 1 plus ARR. Multiply the clock cycle of this clock, not this clock, but this clock, okay? Understand? So you can figure out the clock cycle from there. And this is for mode number 1. Mode number 1 is the output will be high if the counter value is lower than the CCR value, okay? And when the counter equal to that, output will be low. If it's counting up, okay? Counting down is a little bit different, okay? So you can use the formula over here, okay? So for mode 2, remember, you cannot make mistake over here because there's no partial credit. So pay very, be careful, okay? So for mode number 2, it's basically just opposite of mode number 1, right? So it will be high if the CCR, if the counter value is equal. When it gets to the CCR value, the output will become high, okay? And if the counter value is lower than the CCR value, the output will be low, okay? So in this case, you can calculate the duty cycle as well, okay? And the period is the same for mode 1. The period is 1 plus ARR multiplied by the clock frequency right here, okay? And for this case, for the center aligned mode, so you can see that for counting up, the output will become high if the counter value equals to the CCR, right? But when you go down, when the counter value equal to the CCR, the input become low right away, okay? Going up, when the counter value equal to CCR, the output is high. But going down, when the counter value equal to the CCR, the input becomes low. So that's a slightly different when you go up and when you go down. So that's pay attention to that a little. Pay a little some attention to that for me, okay? And then the period, of course. I mean, you see that is almost double, right? Than this case. So you can see in this case the formula is different over here, and the duty cycle is different too. Okay. So I put over here 2 examples for you to play with, right? So in this case, what is the example? The example is they ask something like, suppose the system is 80. Okay, the system is 80, meaning the source. The source here is 80, right? And it wants to create a clock for the timer at what? At 2 megahertz, right? Let me see. Suppose the system clock is 80, and it is selecting the drive the timer one. Driving the timer is 2 megahertz. The following calculation prescaler that slow down the clock to 2 of okay. So if you want the clock that actually clock the timer, the counter is 2, okay, 2 kilohertz. So in this case, it asks you what kind of PSC you use to create the 2 kilohertz clock over here from the 80 megahertz over here. Okay, so you can see it's very easy to figure out. The PSC is 39999. Okay, very easy to figure out about that. So another example over here, you can look over here too, right? So to see, right. So in this case, if you want to divide the frequency here is 4 megahertz, and if you want to create a 1 kilohertz to clock the timer over here, so what will be the prescaler? You can see in this case, you have to divide by 4,000 times, right? And if you divide by 4,000 times, it means that the prescaler is 3999. Okay, very easy. Okay, so lastly, very last thing is about the input capture. So input capture is for you to measure the pulse width, for example, right? So maybe this is the external signal coming in, and if you really want to measure the pulse width of this one, you can use an edge detector to detect this edge and to generate an interrupt, right? And that interrupt will, and at the same time, it will capture the timer value at this time, right? And when you have the falling edge over here, right, you will generate another interrupt over here, okay? And then the timer will capture the new value too. So from the new value and the last value of the timer, if you take the difference, you will know how many cycles, clock cycle, have passed. And from there, if you know the period of the clock cycle, you can figure out the width of this pulse, right? So that's the idea. That's a very easy way to understand the things. Okay, so we have 2 minutes left. If you have any question, please let me know. Oh, why, Sean? Why do we have to move the exam day? Oh, for that one, that's a department. I can't move the I can't move the day.